Okay, in our last video we looked at peptide synthesis, and we said the main goal was to link these two peptides together to form a new peptide bond. And we said the problem was it would do acid-base chemistry, and the carboxylic acid OH is a really bad leaving group. So in the last video I showed you how to use the peptide coupling reagent, DCC, to overcome those two obstacles. But we're not quite done yet. There's actually another problem that I wanted to go over. So let's go into the second problem, problem number 2. And problem number 2 is one that a lot of times students miss. But let's go ahead and think about this. And I'm going to redraw my amino acids. So this is going to be amino acid number 1. It's got this R group coming off. And we wanted to combine this with amino acid number 2 that look like this. However, our main goal was to react these two ends together, right? But if we were to react this with DCC, that peptide coupling reagent as is, we wouldn't just get one product. If it makes any sense, we have sticky ends coming off of two ends of this molecule, right? So what if this nitrogen reacted with this carboxylic acid group? Then instead of getting our correct sequence of amino acids, it would actually be inverted, right? It wouldn't be the same anymore. Or we could have two of the black amino acids react together, making their own unique polypeptide or dipeptide. Or we could have two green amino acids react together. So in many ways, this is kind of similar to the problem we had with the crossed aldol reactions. Instead of getting one nice product, we would actually get a mix of 4 products, which is not ideal, right? We don't want to lose 75% of our yield due to forming 3 unwanted products. So like I said, our goal is to react these two ends together. We don't want these other ends to react. So this OH and NH2 group, we don't want to do anything. So what we need to do is we must protect these groups. And we've talked about protecting groups a little bit throughout the year. There's a ton of different protecting groups. In fact, I used to have a desk copy that went over hundreds of different protecting groups to use for a variety of different circumstances. In this case, I'm going to show you the most common protecting groups that we use in these situations. So let's make a list. And the most common one for amines is called BOC. And it's just abbreviated as BOC. And what this stands for is tert-butoxy carbonyl. Sorry, tert-butyl oxy carbonyl. So you can kind of see the BOC in there. It's a lot easier to write out BOC than to try to explain what it is. But another way of thinking about this is it's got a tert-butyl group, which looks like this. It's got an oxy group, so that's the tert-butyl oxy, and then it's got a carbonyl group coming off of it like that. This whole group right here is called BOC, and it's normally attached to something else. So this is referred to as the BOC protecting group. As you can see, it's pretty sterically hindered, which provides some benefits too. So let's take a look at what happens if we want to install this BOC protecting group. What we do is we take our amino acid, or really any amine for that matter, and we have to react it with a specific reagent in order to get the BOC group on. In fact, there's a couple different reagents. I'll show you the most common one though. But it's BOC anhydride. So it looks like this. So Bock anhydride. Or you may see it written as Bock in parentheses 2O. So that oxygen right here is that center oxygen linking together these two Bock groups, right? So as you can tell, anhydrides are really reactive. We saw this in our carboxylic acid derivative chapter, and it's not going to react with this carboxylic acid group simply because this nitrogen lone pair isn't delocalized and nitrogen lone pairs are better nucleophiles. So it's going to selectively protect that nitrogen group. So let's take a look at what happens. Well, we're going to get the Bock group installed. And we're going to protect that nitrogen. Like this. So this is the new bond that is formed between that nitrogen and our Bock group. And then this whole thing can be abbreviated just as BOC, if you'd like to write it that way. You'll see that shown a lot in your biochemistry courses. All right, so we have that protecting group on. Now we can react this remaining carboxylic acid and with our other amino acid without worrying about the nitrogen end over here doing any sort of unwanted chemistry. All right, and then when you're all done, what we need to do is we need to remove this protecting group and go back to our original amine form, right? And in order to do this, we use a special acid. It's called trifluoroacetic acid. It's kind of like acetic acid on steroids. These three fluorines have a huge amount of inductive pull, which makes this far more acidic than regular acetic acid. So this works really well. Like I said, it's called trifluoroacetic acid. And some chemists will just simply abbreviate this as TFA. It's a lot easier to write TFA than to write out trifluoroacetic acid. So this allows us to install a protecting group and then remove it at our leisure by using TFA. All right, so then the question is, well, we've addressed protecting this amine, and amino acid number 1, but how do we protect this group over here, the carboxylic acid group and amino acid number 2? We also don't want that to react either. So let's take a look at that next. So this would be our carboxylic acid protecting group. And there are a variety of different carboxylic acid protecting groups, but I'm going to show you the most basic one. So let's go ahead and show our amine. Our amino acid, and amino acid number 2, right? And our goal here was to protect this carboxylic acid group. This one's actually more straightforward in my opinion. In order to do this, what we need to do is a Fischer esterification using benzyl alcohol. So this is benzyl alcohol. Oftentimes it's just abbreviated BN. OH. And if you remember, benzyl groups are kind of unique. Benzyl groups always have this CH2 spacer. So this is why we call it benzyl alcohol and not phenol, right? Phenol would have the OH directly attached to the ring. So in order to do this Fischer esterification, we also need catalytic acid. So in this process, what we're going to do is we're going to make a new ester group. Let me zoom out a little bit. And we've got this new ester group over here. So if we want to abbreviate this, oftentimes this entire group is called OBN. This won't do any acid-base chemistry anymore, right? Because it doesn't have any carboxylic acid acidic proton. And it's not going to do any of the unwanted chemistry with our peptide coupling reagent. So it's a good blocking group that we can install temporarily to prevent any sort of unwanted chemistry from occurring. And then just like before, we want to be able to remove it at the end. So we can go ahead and remove it using a variety of different techniques. One is to use hydrogen and palladium on carbon at relatively low pressures. Or if you don't want to do that, you can treat this with hydrobromic acid and acetic acid. Or if you don't want to do that, you can use sodium hydroxide and H2O. Oftentimes, the method you use depends on whether or not you have any sort of sensitive functional groups that are sensitive to acids or bases. So you might want to select the deprotection scheme that is suitable for your amino acid side chains. All right, problem number 3 is just more of a generic business problem. All right, so problem number 3 I'm going to break down into 3 parts. Number 1 is the greenness of these reactions is terrible. Right? If we have to install a protecting group on each of our amino acids and then use a peptide coupling reagent that has low atom economy and then deprotect our amino acids using separate chemistry, we're turning essentially what biology does in one steps into a multi-step sequence, and we're wasting a ton of atoms, right? So the greenness of these reactions is really bad. The offshoot of that is the cost is really high. If we try to do this on a benchtop, right, we're not only using a lot of reagents, but we're taking up a ton of time, and the time of chemists obviously costs money, right? So time is another one that is closely linked to cost. All right, and then the last one is, even if you're a really good chemist, if you're stretching one reaction into multiple reactions, you're going to take a hit in yield, right? So the yield for these reactions tends to be pretty low when we do this. So I wanted to give you a specific example. There's a really remarkable drug called Fusion. It also is called by a few different names. I'm not even sure how to pronounce this other name, so I'm just going to call it Fusion, but it's an HIV drug. And it's a custom polypeptide that's made up of 36 separate amino acids. So custom polypeptide made of 36 amino acids. Now, the coolest thing with this drug is if you take it and you have HIV, it will essentially lower your HIV viral load to an undetectable level. Meaning if you're taking this drug responsibly, on time, things like that, essentially you'll test as being HIV negative. It doesn't mean you're HIV negative, it's still in your cells. However, you don't have any free virus floating around inside of your body. This is typically a drug of last resort, and you'll see why here in this next step. It costs about $30,000 per year. And the reason it costs so much to make has to do with all of these things that I talked about over here. If you want to make this drug, it's going to cost a lot. It's going to take a lot of time. You're not going to have very good yields. And you have to take this drug multiple times, I think a day, or maybe it's once a day. It's an injection. But your liver clears it out pretty quickly because your body typically isn't very happy with these custom peptides in there. So the last solution I wanted to talk about is actually used in the production of Fusion. And the solution is to automate everything. If we can automate everything, as much as possible that is, then we can start to lower the cost, we can lower the time and improve the yield. The greenness is still not going to be very good, but at least we can lower the cost a little bit. So that's what we're going to talk about in our next video, is how we do kind of automated solid phase peptide synthesis.